check the names of the students, and you is not there. So you are a guest student?
No, I start here.
Oh, all right. But I thought that you want to sit in the class.
Yes.
Oh, that's good.
So, sitting class.
Sure, please do so. But if you come today, then you have to come every day.
Yes, sure.
That's the contract. So I can start.
Yeah, you can start.
We will leave us.
I will come back to the office.
I should come to your office. Sorry,
I
I
will
didn't.
come back to the office and you can start.
Oh, yes, okay. And now I missed it. All
Have
right.
a nice day.
You too. Take care. So my name is Mehdi Hossein Kuchek is my surname. So I'm a professor of econometrics, and I just like econometrics. So sort of whatever is actually around financial theories, and also econometrics by itself. My main field is time series analysis. I did my PhD some years ago. So my first and second supervisors were Michel Binder and Uwe Hassler. So well, I liked what Michel does, so it's very interesting and so on and so forth, but then after some years I sort of moved a little bit away from what he does and then focused more on time series analysis, so this is what Uwe Hassler has probably, you have had a course with him, right? Very good, okay. So, well, I have worked with him for many years, we have a lot of papers, we have had a lot of fun actually in the last years and so. So that's a bit of my background. Well, I mean, oftentimes when I come here, then I try to learn the names of the students, and that's actually a bit hard. But then I sort of will try. You know? So what I will do so that I remember your names is that I will write them on the corner, so that I look at them as, because I want to talk to you as time passes. So, what is your name?
My name is, but it sounds like number two. You can sound like two. TFU, TX, and U.
So TH usage.
Yeah.
Oh, like this.
No, it's pronounced like two. Yeah.
Simple. Okay. So because of the H, I thought it would be simple. So you're
My name is Tuyền. The sound like tree, but no system here, just only
like this.
Tuyền. T-U-Y-E-N.
T-U-Y.
E in the time.
Oh, sorry.
N.
N.
Yes.
Three N.
Yes.
What's the word in Vietnamese for water? It's the same.
No,
Not water. Thủy water.
But last year when I was, so last course when I was here, I had a student, his name was two, but not H without. And then when I sort of, I showed a lot of interest, sort of learned some words and so on and so forth. And then by the end of the course, he gave me as a present some Vietnamese books. Which is sort of, it's just unbelievable. I mean, it's not possible. But I mean, I have the books anyhow, so. So,
My name is Quang. Q U A N.
oh,
Yes.
you are you. Like this?
T U. Yes.
no. His mean H-I.
I-E.
So, two,
My name is On. On.
On.
On. Yeah. Sound like one. You can say that. One. One is okay.
one.
Yeah.
So you have 1, 2,
Same, same. Same, same.
1, 2.
and this is my name, and this right here, my first name. So Mehdi is my name. Alright, my first name. I suppose these were all your first names, so you have my first name. Alright, good. So I know a bit about you. And I sort of in the meantime understood that you have had the course of Uwe Hassler, so which is good. And I suppose it was a lot of theory. So what I will do actually in this course is sort of a combination of data work, which means a lot of programming in Python, and also theory. Yeah. I mean, the thing is that, if you don't know the theoretical backgrounds of different models, and if you don't have them fresh in front of you when you start doing data analysis, then you will do something oftentimes which is not sound. You may actually do stuff which are not really okay. By chance, you may get some results which are good, but if you know sort of the theoretical stuff, then you, first of all, when you do apply work, then you will do better ones, number one. Number two is that, so if you are interested in sort of developing theory and getting ahead, then you have to always remember them. You have to remember the tools, the methods, and so on and so forth. So what I will do today is, I will actually start with reviewing some stuff from Uwe Hassler's class. All right. Well, I mean, the way I see time series analysis is sort of very much like Uwe Hassler. So he was my he's my co-author. I learned a lot from him. I know all of his books. We are collaborating on a new book together, and so on and so forth. Sort of the stuff that you will hear from me are not actually different in terms of notation, in terms of flow, and so on and so forth, from that of Uwe Hassler. Yeah, so that will be very similar. All right. So that's sort of a standard. And maybe in terms of organization, so you see that we have these stuff, and then there is some reading material that we have here. There are four actually sets of the slides. So we have volatility, well, the arch-Garch models. I will tell you the theory, but I suppose you haven't done data work, so we do data work with them. So sort of how to estimate a Garch for, say, whatever financial market index. All right. And then we will go to Markov switching models, which probably is new for you. Potentially, you know what a structural break is. All right. But then oftentimes in practice we don't, I mean, sometimes you know when a structural break takes place. Sometimes you don't. All right. And then sometimes the structural break is not for sure. So maybe, maybe not. So it becomes stochastic. And sort of this Markov switching model is actually the name as it says, so they are switching between different types of. I just saw that you're coming from.
Could you talk louder a little bit?
Yeah?
Yeah,
It's quite low.
yeah.
You know what I can do? I can come here.
Face to face.
Yeah, well, I mean, closer I can't come. So. But what I was actually saying is that, so if you, what was I saying?
Say about the stochastic?
Yes, well, thank you very much. Well, sometimes the structural breaks are not known. Well, the date is not known. Or, so to speak, you don't know whether you have a break or you don't have a break. All right, so sort of maybe a stochastic. Maybe with probability 1, you have a contraction, with probability 0, well, that would be a singleton, but maybe, say, 0.8, you have sort of a low mean growth in, say, GDP, with probability 0.5, you have a high. Right? So sort of, you may actually have regimes that are probabilistic here. So this is indeed this chapter about the, well, sort of that is the Markov switching model. So that's about what are the structural breaks, but that's probabilistic. I will tell you a bit of theory, not much, because it could be a bit involved. Right? So I will give you a bit of theory with a very simple model, but not in dynamic setup and so on and so forth, because the likelihood becomes involved, and well, I mean, we need actually many days to write down maximum likelihood for such type models and then be able to estimate them. So I will actually take it easy. So the idea is that you understand what are Markov models, so Markov processes. So I will give you a general understanding on them, and then how to apply them to, well, regression. All right, so that's sort of what we will do. From different angles, so the slope breaks over a linear regression. Maybe that you have a heteroscedasticity of certain form, let's say low variance, high, variance, profile, low, medium, high, sort of three regimes, and so on and so forth. Or a combination of the two. So that's sort of what we will do in the Markov switching, basically. So that would be a topic which is potentially very much new for you. You haven't seen it before. All right. Well, the first one you have seen the theory. I will review the practice. So the Markov models are new to you. And I'm sure to tell you the theory and then do some data work. Then we have the MPT, right, which you also know. All right. So that's portfolio theory. But then potentially you know the theory from the angle of what is sort of which are nice essentially. So I really much love, or very much like them. So sort of from the choice sort of theoretical point of view, which is sort of fine. But I mean, what I will do is I will do really portfolio theory, or sort of we'll have a lot of data and then pull a portfolio out of it. So we'll with Python. So we'll do programming. Well, with a bit of theory, that's the efficient market hypothesis. So I will review it. I know that you know that, but then I will do also a little bit of testing. So how to test for efficient market hypothesis in data. All right, so using data. The last chapter you also know, I suppose, factor one. So you know the theory. I will again review it, but then go and then do some programming, sort of implementation of those. So these are the topics that we have today. Essentially, not all of them in this lecture.
Yeah.
Maybe a start, right? But as I said, so a prelude will be a review of time series models. All right? And I just sort of I use these time series models to understand who is who. What do you know, what you don't know. All right. So what is actually missing? Maybe I just add something here and there in terms of understanding and implementation of concepts. All right. And then we go on. All right. So that's sort of what we do. Now let me talk a little bit about the organization of this sort of material that we have here. Well, look, here we have a folder which is empty as of now. All right. But then I will fill it right now. All right. So that you have some very simple idea of. I mean, these assignments that we have today, I will mostly do them myself. But they will just help us with getting essentially the material going. So please download that and have it on your file or sort of machines. All right. So that, well, we could start essentially. We'll do those exercises as I said today, both the theory and also some programming. I will do with them, and then we will continue. All right. So we just use them sort of today's questions for getting things going and rolling. All right. So that's a review question. This is a regression which probably also is new for you. We're going to give you an idea of that on that. Well, I mean, part of this sort of course is also, well, I mean, as the name implies, it is a data science 2 class. And then, I mean, to do data science, you need, well, a bit more than the usual simple regressions, which, well, we will review and understand, but I will do a bit more. All right, so a bit, not much. All right, as much as time allows. But let's just start. Okay. So, well, I mean, here we have. Well, I just want to do these questions. So I will review the material using these questions. Right. Let's just start with A, part A. So what does it say? It says we have a random variable which is positive with probability 1. Right, so that's sort of what we do. Maybe I could become a little bit more careful here. And then also assume that the expected value of absolute value of x, where x is positive, is bounded. Alright? So, well, it means that the expected value exists. So it's not a Cauchy, a standard Cauchy random variable. It's a random variable whose mean exists. Alright? Well, even if the mean doesn't exist, then well, we can still proceed. But so let's, for simplicity, actually assume that. Alright? Now, and then we know the probability of x being positive is 1. also have a sort of a crisp deterministic number A, which is positive. Right? So these are all we have. And then we want to show that the probability that X is smaller than A is at most the expected value of X divided by A. Yeah? So that's sort of something we know. So these are the assumptions. All right? So assumptions. And this is a result. And then you will know what is it for. Very simple. All right? So when we do the second one, you will know what it is. That's a true decision. You know the name of this inequality? That's an inequality. Have you seen it before?
Yes. What?
What? That's called Markov.
Markov inequality.
That's the Markov inequality. Right? So this is Markov inequality. Alright. So, and then this question actually asks to prove it. So I want to prove the Markov inequality. Okay? Well, that's a very simple indeed result. So you mentioned that you know that the name is Markov inequality, so you have seen it before, I suppose. Yeah? In which course? Uwe Hasse maybe? Or maybe somewhere else?
Yeah. Michael Winter also.
Michelle Binder also uses
Yeah.
it. Okay, so that's right. So that shows up. But did they do the proof for you? No. So nobody proved it. I will do it. I will prove
Thank
it.
you.
Alright? That's actually very simple. Look, a lot of the stuff that we do here may actually sound a little bit involved, complicated, but actually they are not. Right? So most of the stuff that we do
Cảm ơn đi, cảm ơn sách đấy. Nghe nhiều.
introductory class. So it's not actually high tech, it's not rocket science. I mean, you just need to pay attention, think logically, and you will get things. Right? Well, I mean, let's actually understand what these guys are. Right? So what are these? So this says that the probability that X is at most A is at most expected value of X divided by A. Yeah, so that's sort of what it says. But, so that's a random variable, and whenever we have a random variable, then we always remember a PDF. Alright, so a PDF always helps us understand the behavior of a random variable. Apart from that, then we also understand a CDF. Alright, so that's the cumulative distribution function. That's the integration if X is continuous. Well, let's assume that X is continuous, that is easier. Integration under the curve of PDF from 0, here X is positive, up to some certain value X, essentially gives you the probability that X is smaller than that value, and that becomes the CDF. Essentially what we have here is the CDF of X at A. Right? Then, well, that's the probability is at most this. Okay? So which is actually, as I said, so it's a nice tool. A lot of the stuff that we do when it comes to asymptotic theory, we start with that. But let's now remember, or sort of draw some pictures so that what you see, what is that? Alright. Well, so let's say we have a Cartesian sort of setup. X is all of the values the random variable X takes. So that's the support of the random variable X. And let's say this is 0 and this is 1, and then let's draw the CDF. The CDF starts at 0 and then goes to 1. Alright, so this is CDF, right? Very good. And the probability that X is smaller than A, essentially, well, let's pick some number on the horizontal axis. Let's say A. Alright? So this is the probability that X is smaller than. Right? Well, that's sort of what you know from basic probabilities here. But indeed, so I can take that out. Alright. So here what we have is that the probability that X is smaller than A is integration from 0 to A, alright, of, well, PDF of X dx. Well, that's essentially the other algebra elements. Alright, so that's sort of what we have. Well, so that's sort of the left-hand side. On the right-hand side, we also have the expected value of x, which is what? Which is the integration from 0 to infinity, right? This doesn't look alright. Sorry. Or it's the other way around. Alright, so we just had the, alright, but we have essentially those stuff, so that's the probabilities and so on and so forth. Sorry, that was a mistake. I will correct it also in one line. Alright. So that's sort of the probability of x being smaller than a, and naturally here we have the probability that x is bigger than a, is integration from a to infinity, well, I mean, that starts from a of f of x dx. Right? So that's sort of what we have. That's what we have on the left hand side. Let's look at the expected value of x. That is, well, the same except that it is a weighted sum of all of the values that x takes, and the weights come from the period. Right? So that's sort of the expected value. Okay? Well, I mean, now let's actually work on this. A little bit work on, so let's sort of just scribble a little bit with that guy. So that we can write as integration from 0 to a, f of dx, plus integration from a to infinity of x, f of x dx. So just break the integration from 0 to infinity to 0 to a to infinity. So these are two pieces. Sort of the, I mean, that you know from calculus. That's sort of from algebra. Right? So I sort of break this into these pieces. Yeah? So far, I didn't do anything out of the ordinary. Yeah? I will write something, and I want to know what you think about that. So here I would like to write this as this being bigger than or equal to integration from a to infinity of x, f of x, dx. Do you agree with that? I mean, do you think that this inequality is okay? Doesn't make sense. So what we have, there's sort of a positive value plus another one. If I take one piece off, then I'm left with a smaller value. Right? So if I set this off, then I get a smaller value. So this is smaller than the sum. Right? So this is 1 plus 2, and this is 2. Right? So 2 is smaller than 3. Yeah? Yeah. Now I write another inequality, and then you check if it is alright or not. So here I will write that this is integration from a to infinity of a and what about this? Does it make sense? I mean, at times I may write the stuff which are wrong. What is your name?
I'm D.
L-I-N.
D-A.
D-I-N.
D-E-A.
D-E-A-N. Dean. Oh, you are the dean. Dean. D-E-A-N. Is it okay? Can you explain why? One of you. So the only thing
Because
that
Smaller than x.
yes, that's true. So, well, summation, but it's a sum integral. And then a is smaller than x, so the whole thing should be smaller than the other. Right. So far, so good, right?
Yep.
Now, well, let's see what happens. So that's a constant. Comes out of the integration. And then this is equal to a integral of a from a to infinity f of x dx. Right? Well, I take a off because that's a scale. So what is this?
Probability.
So this is equal to a, and probability that x is bigger than a, right?
Yeah.
Now let's see. So this is expected value of x
Oh.
is bigger than this. So let's rewrite it. So here we have expected value of x is bigger than or equal to a times probability of x being bigger than a. And if I rewrite it, then I get the result. Yeah? Well, that means that, well, let's divide both sides by 8, and here we'll have the probability that x is bigger than a is smaller than or equal to the expected value of x divided by a. Alright? This is very simple, right? Well, I'm sure you could reproduce this if you were thinking of it. By yourself. So Dean, you came a bit later. So maybe I'll just tell you who am I. My name is Mehdi, and I'm here for 2 weeks with you. I will teach this course, and that's a combination of theory and applied work. So well, today we'll review a bit of the stuff from previous courses that you have had. And well, as time passes, then little by little theory.
Chị tìm muốn xin một tờ giấy. Xin trong cái đốc.
The other work is
Lấy đi
Python.
cho mà.
You need to have Python to be on your mission. I may do a bit of a startup, but I know them. So let's see how things. I just need something very brief. Alright, so that is the mark of in the theory, as you have it here, and then we have a proof for it. Okay? Now, what other inequalities do you know? Now that we have them on a step, maybe we can jump a little further. What other inequalities do you know?
Jason.
What's that?
You say that another in
Sir?
so you say that if we know another
Yes. What is Jensen's inequality?
FX smaller than projections and expectations.
Very nice. Exactly. Very good. Okay, so you remember that. Alright. So you have a convex function, and the expected value of that function of a random variable is smaller than the function at the expected value. Yeah. Let me tell you something about where Jensen's inequality comes from, graphically. And then you know that.
No, because in the course of
Some.
derivatives,
Uh-huh.
another professor used that to calculate or for the stock option.
Sure.
Yeah, so
That's true.
yeah, they just mentioned about Jason
Okay.
inequality that happened.
Jensen.
I will give you some picture, and that will stay with you for the rest of your
Yeah.
life. Alright? Let's say the other. It's not about probability theory or random variables and so on and so forth. Well, let's say we have a function like so. Is it convex or concave?
Concave or convex?
That's convex. It's so bold. It's a fault. Okay, it's like this. Right? And then let's say we take two values of this one. A and B. Alright? That is what we have. Okay? So that's one value and that is another. Right? So the beginning and the end. Well, I could actually look at many points, but that doesn't matter. Alright? Where is the average of A and B? In the middle.
No.
Average is always in the middle. It's here. Right? So this is A plus B divided this is the value of the function at this point is here. Right, so this is the value of this guy. Right? Well, that's the mean of the values. Right? And then well, let's look at those two. So here and here, then we also have two values. All right? That's sort of the values of the function. And where is the average of the two functions? It's also in the middle. Here. Right? So that's the mean of that. Alright, so the mean of the function at A and the mean of the function at B. Alright? So when we use this is a function f, then this is f of A plus f of B divided by 2. Right? And the value that is black is f of A plus B divided by 2. Which is bigger? That's true. This is Jensen. This is Jensen's inequality. Right? But the average of the function is bigger than the function at the average. Okay? Well, of course, we can make it. I could approach this from a major theoretical way. Sort of, I could do it a bit more probabilistically way, in a more probabilistic way. But that's the idea. Okay, very good that you know the Jensen's inequality. What other inequalities do we have? Can I borrow this? You take notes. So we just, we have the proof of Markov, alright? And now I can wipe it. Okay. Alright, so very good. So we remember the answer. Do you remember this inequality? You can leave with the rest of the name. You remember that? Probably you have seen it too. Yeah? And that sort of shows up very often here and there. Right? So it's sort of another. And what does it say? Well, you may have forgotten. Let me just write it a little more. Right? It says if you have a random variable x with bounded variance. Right? So here we had the first moment bounded. So now we have some variable which has the second moment bounded. So we have x such that the second moment is bounded. Alright. This guy actually says that the probability that absolute value of x minus mu of x is bigger than some number a is always smaller than or equal to variance of x divided by a squared. So that's Chebyshev. Right? So probably you remember that. Now that I write. Alright, so that's sort of what we have here. Does it actually have some similarities? Seems like. Alright. Now let's actually see it. Look, it says we have a variable which is positive. Well, it's an absolute value. A positive random variable. This guy in absolute value is positive. Maybe that's a variable, or sort of some number a, real. Then it's bounded by the variance divided by a squared. Well, here we have the expected value of this divided by a. So that was the Markov, which we have in the, well, we proved it. We know how to actually work with that. But let's see whether we can actually reach this from this. Yeah, so we have that, and then I want to basically go from, well, to that. That's right. Yes. Very nice. So this maybe, so instead of this x, I would just move it, well, instead of that, let me write Z. Alright? So, yeah, this, and then Z. So that we don't mix them. So here. Z is a positive value. Right? Now, when we match those guys, then I will actually call this Z. Alright? So that's my Z. Alright? Which is positive. Alright? So here what we have is probability that Z is bigger than A. Well, of course, this is equal to, well, Z is a positive value. It is like this bigger than A squared. So I simply take it to the power of 2. Well, it doesn't make any changes. Right? Because Z is positive. If I take it to the power of 2, then, whatever, that's the same in the space. The probabilities are the same. Alright? So that is what we have. Well, that's also a positive value. Bigger than some value which is positive. Alright. This is smaller than or equal to the expected value of Z squared divided by A squared. Right? That's sort of what we have here.
Variance.
That's true. Right? So because this is x minus the mean of x to the power of 2, and then taking an expected value, which is the variance, and that's change. Yeah. So you see, from a very small picture, we're playing around with the integrals. Then we have Markov. From Markov, then we have change. And we can continue and then do more and more. Right? But we'll stop. Okay? Good. That was sort of a bit of review with logics, and I'm happy that you talked to me. And please talk more. So maybe I should ask you questions and pause, and then you do some stuff. Sort of. Let me fix the inequality on line. Sorry for that. And then we go. Alright, so that should have been bigger. Alright, so that's now I've just corrected the sign. Alright, so far so good. So we remember Markov, we have Chebyshev, and now we can go on to further stuff. Alright, so let's actually start with this very simple model. So we have a dynamic model, that's an AR1 model, alright, where rho in absolute values is smaller than 1, epsilon is RIU0 sigma squared. I love this job. Alright. And now we want to do some sort of some other stuff, okay? So this actually tells us what about that? What is that for a condition? What do we call it? Yeah, that's rho. And when rho in absolute values is smaller than 1, then what happens? What can you say about x, t as a process?
Stationary.
Vt is stationary. Thank you very much. Okay. So it's a Vt stationarity condition. Alright? Very nice. And now what we actually want to show is that x bar converges to this quantity. X bar is the average. So mu divided by 1 minus rho. Alright? of semester. Look, I mean, here we have xt to be equal to some mu plus rho xt minus 1 plus epsilon t. Epsilon t is IID 0 sigma squared. Absolute value of rho is smaller than 1. Well, which means that we have weak stationarity. What does it mean that we have weak stationarity? It means that the expected value of xt is some mu of x, which is time invariant, doesn't change with time. And then we know that the covariance of xt and xt minus h is gamma h. Right? That's the notation of Huber-Hassler.
Yeah.
But this actually depends only on the time lag, not on time. Right? And then we also know, well, of course, gamma 0 is, well, I mean, the variance is also time invariant. Alright, so this is for any h, positive and negative, and so on and so forth. So for any h, including 0, which is indeed the variance, this quantity is just time invariant. The variance is fixed, and so on and so forth. Right? So just time back, not time. These are the big decisions. You had the course of Huber-Hassler in December. Yeah, so 6 months ago or so. It's not so long time ago. These were the conditions. Well, I mean, let's actually use this. So here we have expected value of xt equals expected value of what we have on the left-hand side. Mu plus rho xt minus 1 plus epsilon t, which is indeed mu plus rho expected value of xt minus 1 plus expected value of this, right? Well, expected value operator is linear, right? But that's a linear operator. So expected value of the sum is summation of the expected. So what? I mean, this is weakly stationary, so this is mu x equals mu plus rho mu x. Well, I mean, this is t minus 1, but who cares? That's weakly stationary, always the expected value for whatever value of t is mu x. And then this is 0, and that implies that mu x, which is the mean of x, is mu divided by 1 minus rho. So that's the theory. Right? But what I asked you actually on this is also theory, but it has something to do with the data. Right? In the sense that, well, let's say you have t observations. Alright, so on this guy. Alright. So here we have, say, xt, t from 1 to capital T. And these are observations. So a sample. Alright, so random sample set. And then we want to know where does this converge to? Alright, so that's the average. Average of the sample. When the t grows, it becomes larger and larger. Then we will indeed get, well, do we actually get to mu x? Well, potentially yes. Alright. But indeed, those assumptions are important. That rho is smaller than 1. I mean, this can be, the variance can go up and down. As long as it is bounded, it's not an issue. Well, that sort of simplifies matters. But we want to just show this. We want to show that the average of the data actually gets us the true expected value. Can you show that actually before I go on? I don't know. Can you show this? Do you understand this notation? The arrow with the P on top. I'm just asking so that I know. Yeah. You wanted to tell me something?
So like, I'm not picture for it, but it means that we understand the
very pen. So let me see how to approach it so that you don't forget. Alright, so do you know sequences? Yes.
Yeah.
So those sequence of natural numbers. So there's 1, there's 2, the other one, 3, and so on and so forth. Where do they land? Well, there is no limit essentially. But if you have a sequence of say a n equals 1 over n, and where does that converge to?
Yeah.
So then grows, becomes larger and larger, then we land here. Why?
Because 1 over a big number.
N becomes a very big number, yes.
So
1 over the big number will
It's a very small number.
yeah.
So we get closer and closer to 0. So this is something you really know, right? So the inverse of a very big number is a very small number. So indeed, in you, inside you, right, in your brain, here, not there, inside you, then you have a logic, you have some tools, you have some general understanding of numbers. Right? And you know that this sequence goes to 0 when n becomes large. Okay. Now, well, I mean, here is also like I have an arrow.
That
And
makes
this
sense.
is actually a sample of size t. So I want to know what happens when t grows, when t becomes larger and larger, then this is a sequence. So first you have one number, the average is the same as that. You have 2 numbers, and that becomes the average of that. Then you have 3 numbers, and so on and so on and so forth. And then we want to know what happens, right? So does it go to 0? Does it go to 10? Does it go to mu? Does it go to rho? Or does it go to this? Yeah? That's the same. Alright? Now the thing is that, so here you have your own logic, you have your own tools. You said, alright, so the inverse of a very large number is a very small number. So there are tools that you have in your brain. Right? So they are in the back of your mind. Something. Right? And then they help you to basically go on with telling me that the limit is this. So to be able to establish this guy, right? Well, this is a random variable. That's a sample. So this is sort of the numbers are not the same. We have this random sample, and then the average would be a little bit problematic. Sort of goes up and down. All right. Well, indeed, we wanted. Well, of course, it goes somewhere, but that's the hope that we have. And the average will be some value which matches the theoretical average. All right. So that's really what we have.
That makes sense.
But because this is a random variable, then the convergence requires some other tools. Some other tools. And these are the tools. So these are the tools that we need to be able to establish that this is actually converging somewhere. Right? But because this is a random variable, then we say that the convergence is in P mode. That's in the probability mode, or the convergence in probability. Alright? So, well, indeed, I mean, so that goes to mu x. So this is what I want to show. Alright, so that is what we want to show. But then, well, I mean, well, of course, you know this from your calculus classes or real analysis, whatever that you have had in your. I just want to know your name. I can't teach without that.
Hui. H-U-Y.
Like that.
Yes.
Let me see. So we have 1, 2, 3, 4, 5, 6, 7. Where was this? Cool.
Yes, yes.
Very nice. Thank you. So actually what we know from real analysis is the following. So that's the limit. Let's put the limit n. So here we know that a n smaller than any positive value you may wish to basically choose. Right? So, well, so to speak, then n becomes very large. Then n, well, the sequence value, which is 1 over n, when n becomes larger and larger and larger, then a n becomes as close as possible as the limit. So it means that the distance of this becomes smaller than anything you sort of can think of. Right? Well, so this a n converges to 0 as n grows is the same as saying that a n is closer and closer to 0 with some, well, with n indeed growing. So the absolute value of this difference is always smaller and smaller than some positive value. Alright, so that is what we have. Now, well, let's see what, how can we actually turn this to this definition so that this we understand properly. So here, because it's a p convergence mode, then we would say that the probability that the absolute value of x bar t is away from mu x, alright, being bigger than any value epsilon, alright, converges to 0 as t grows. Now let's understand one for any positive epsilon. Right? Epsilon is a positive value. Alright? So here what do we have? That is the sample average minus the true expected value. What is the distance? How far
Okay.
our average is through the sorry?
No, I forgot. Not the mean. So,
Sorry.
I just remember about the mean, but maybe not correct. Sorry.
No problem. That's all right. So maybe I finish my arguments and then you ask.
Yeah.
So here what we have is the distance of the sample average from the true parameter, or the true mean, being bigger than any positive value is 0. So it means that there is no probability when t is large, such that the average is not on the true parameter, or the true mean. Okay. So this definition in the deterministic setup becomes this in probabilistic setup. Right, so that becomes what? This that we write here is equivalent to that. Alright? Like this that we wrote here was equivalent to this. Alright, so they're the same. This is the same as that, and this is also the same as this. So if I show this, then I show that. But this is also consistency. Of course we know what is consistency. So here what we are going to show is that the sample average is consistent for the true mean. Well, it converges to the true mean in probability. Alright. Now you should also see why did I tell you what is Chebyshev because for establishing P convergence always requires Chebyshev. Because that's a probability of an absolute value bigger than something smaller than the variance divided by a squared. Right? That's sort of what we have. Good. So now let's see. What are we going to do? Okay? How can we actually get sort of approach this? So this conversion to that AP mode is equivalent to that. Right? Alright, so again, I can buy this. Alright, so these are some when essentially time passes. Wait a moment, is there anybody who wants to do a PhD after this? What do you mean by me? Everyone? No one?
I think about that, but I haven't decided yet when to actually start.
Oh.
Yeah, because maybe I think I will need to find a job first to have enough finance that I can finance the next few years of PhD.
Well, maybe you can get a stipend.
Yeah, but I also want to
To work?
Yeah, like have my own money instead of just relying on
Of course.
all
it. Yeah, well, sure. Well, I mean, thank you very much for so openly sharing your thoughts. Well, I mean, if you want to go towards a PhD, then you need more and more such tools, and you learn them as time passes. And so, these are the beginning, but there are more, and depending on what you want to do. Whether you want to see econometrics, finance, or whatever. All right, well, let me basically continue here. Look, this guy can be applied to that. Right? So if I want to show this consistency, then I can show this. They are equivalent. This definition is the same. Now let's go with this guy. All right.
Oh, variance.
Right. P minus mu x. All right. Which is that? Being bigger than epsilon is smaller than or equal to. Oh, what? I mean, variance of this, because that's x bar minus that. Well, we have to actually check whether this is indeed the same, what x t bar has the mean. Alright, so let me just write. So that would be, well, this bigger than that is smaller than or equal to the expected value of x t bar minus mu x to the power of 2 divided by epsilon squared. Right? That's sort of what we have here. Now the question is that is this the variance? Is it not? Well, can I? So that's the question. Is it equal to the variance of x t bar divided by? So can I, instead of this, write the variance of x t bar?
Yes.
Why?
That's a good formula.
Yeah.
That's
Alright. That's true. But this is mu of x. This is not mu of x bar. Yeah? But look, I mean here we have x, some random variable, minus its mean. If you take it to the power of 2, and then take an expected value, then you get the variance. Alright. So here I have x bar minus mu of x. Alright. So if this mu of x is also the mean of that, then I can say that this is correct. So let's check. Alright. So what I'm actually doing here is that I want that you pay attention to all of the details of, so that the variance is not what? I mean, variance of x minus 2 is not the variance. Expected value of x minus 2 to the power of 2 is not the variance, only it will be if the mean of x is 2. Right, so same. So let's check. So let's look at expected value of x bar t. So that's expected value of 1 over t summation x t.
Yeah.
T from 1 to t, right?
Yeah.
And that is 1 over t summation expected value of x t.
Yeah.
And that is 1 over t times mu x, which is mu x.
0.
So that's what would be t times expected value divided by t, then essentially, so then this is the variance. Well, so far so good. Okay? So that is what we have. Now that we have the Chebyshev, then I can write that. We don't need it anymore. We could approach it with the mark of 2, but that is a bit easier or more fun. So this then is smaller than the variance of x bar divided by epsilon. So let's calculate the variance of x bar. So this is the variance of 1 over t summation x t. Well, this is t from 1 to t, so don't write the limits. Yeah. So, would you please continue? Thank you very much. I'm here, right? Be careful.
What is it?
can actually come to the board if you wish. Yes, I just picked you at random. So, can I give you this? And then you may wish to help too?
You already done.
We have a different answer to people, we can like.
But wait a moment.
What is square variance of
Is this
summation?
equal to that?
Not really.
Not really.
It reflects it.
Exactly.
Yeah.
That's true. So, I would mind.
Yeah, of course.
So, but I just want to remember sort of you. Yes. So here we have a constant, right? That's a variance. So let's deal with the constant first. But thank you very much. The thing is that the average is not the expected value. The average is just an average. That's a value.
It's the same, something like sample.
Average.
Just different value.
Expected.
Homology,
That's
right?
true, yes.
Okay. One with the t-square.
Very nice. Thank you very much. So this comes out as t squared.
1 over t square.
It's very important. Variance of summation of x. Now what do we do with this? Well, with the expected value, then we had also this. This came out. Here also first came out. And then, so I could swap the variance and expected value. So can we do that too? Where's the variance of this? So let me write with red here. So I would just write here. So let's say we have two random variables. Say ax plus b1. Variance of a linear combination. It is equal to
T square variance of x.
right plus
B square variance of y. And plus 2ab covariance.
that's true. So that's
Correlation.
AB
AB, yeah. Correlation or
covariance of
covariance. Yeah.
plus AB covariance of y and x. Right, so all of the combinations. This to that, this to that. The covariance is symmetric.
It's
And you
symmetric,
said
so
that
we
this is
have two. Yeah.
twice.
Yeah.
So, but that is also very important that you remember that this is what symmetry. Thank you very much. So now I'm here with you. So here we have a summation. Right? Maybe for simplicity, let's write it like this. Summation, variance of summation of what? Of x1, thank you very much, x2 plus xt. Yeah, so that's the variance of also a summation. Like we had there, then we have the variance of the first plus the variance of the second xt plus which
Covariance.
one totals? One
One,
totals?
yeah.
Yeah, but we also look at the covariance of this and that. X1 and X2. X1 and X3. All of them. Yeah. And X2 and X1. X2 and X3. And so on and so forth. We have to look at them all. So let's do this step by step. So that will be no loop.
Yeah.
Then 1 over t squared is variance of x1, the first, plus variance of x2, plus variance of exactly the last. Right? Now plus covariance of x1 and x2. Right? There is more. Yes. Yeah, but then now we have covariance of now x2 and x1, right? And so on and so forth, right? So we have to basically write all of the covariance. And let's write it. So covariance of x2
just regular check, frequently checking, no, not related to.
Oh, so that I'm. Is it okay? Sorry. Good. Take my pen. So let's look at all of these. Alright. So indeed, I just want to. That's a very ugly summation, right? So many simplify. Yeah, so I will simplify it for you so that you see how nice it could be. Yeah.
Zero. IIT,
Alright. So look, this is variance or covariance of x1 with itself. And this, well, I mean, it looks like that we have covariance of x1 with itself and with all of them. We have x2 with x1 itself and everything else, and so on and so forth. Right? So every variable with all of the others, including if I'm x1, then with me and all of you. Right? So that's sort of what we have. If we look at this in a simpler way, all right? How many terms there are?
T squared.
That's true. Yeah. Very nice. Right? So this is, we have say x1 and x1. Right? So that's the covariance. Very nice. So then we have covariance of x1 and xt. Right? So this is this and this row. Alright, so these are t minus 1 plus another one becomes t. T minus 1 plus another one becomes t. T minus 1 plus another one becomes t. So you can write them all here. So that would be covariance of x2 and x1. Covariance of x2 and xt. Alright, so let's maybe write it as a matrix.
Đúng rồi.
And then here we have covariance of and
Matrix.
x1,
Variance of a matrix.
covariance of xt and xt. So we want to sum all of these elements. So that's a weakly stationary process, remember. This is gamma 0. Right? What is the element at the location 2, 2? So this is at 1, 1. Right? So, well, I mean, what is this then? Look at this.
Gamma
Very
1.
nice. And what is that?
Gamma T minus 1.
What is this? Oh, sorry. This?
T minus 1.
This?
T minus
So this is row 1. So row 1, column 2. What should I write here?
2. No.
Here? Here? Do you see a pattern?
Yeah.
What is it? I want the summation of all of them. So look, what we have here actually was summing these. These are variances, the main diagram. And then this one looks at this, and so on and so forth. Right? The second line that starts with that jumps and then goes to here. Alright? Sort of it's very ugly way of counting. Okay. same elements together. That becomes easier. So that's a t by t matrix, so I have t gamma zeros. Right? So this is 1 over t squared, remember? So here we have equal to 1 over t squared, t gamma zeros. Right? How many gamma 1s do you have? Do we have a mathematician in the class? Somebody with math background? I'm just asking. Do you have a math person? Somebody who did math? Bachelor in math? No. Alright, that's it. So tell me, how many gamma 1s do we have?
Also, I
T
think
minus,
T
two
also.
times T minus 1, I guess.
Two.
The one before and not the one upper and lower, then we up and then middle, like so. So 2 times T minus 2, 3.
Yeah, sorry, 2. How many gamma t minus 1s do we have?
2. This one is 2 T minus 1.
So that's sort of what we have here. So let me write it as a summation. And then sort of open. So here then we have 1 over t squared. Well, that is t minus 0. Correct? Well, I mean, let's maybe write it like t gamma 0 plus twice summation t minus j gamma j. So that's j to j runs from 1 up to t minus 1. Good. So that's the variance of the average. Do you know what is long run variance? Well, long run variance actually includes the variance and also all of the covariances. So this also looks like it includes variances and all of the covariances. So it has something to do with the long run variance. And that's actually conceptually, I think, important. Because why do we have something which we call it variance, and why do we have something we call it the long run variance? Long run variance actually is all of the covariation, or all of the variation, let's say, that a person has. That's why we call it the long run variance. Alright? And indeed, well, I mean, X bar includes all of the sum. It includes X1, includes X2, all of them it includes. So if I look at the variance of that, because it includes all of the random variables, then the variation of the variance should basically show up. And all of the covariations should show up here. Alright? So here the average has something which is somehow interesting in the sense that it looks like to be a little bit related to the long run variance. But now that's a very simple formula, as you see. Let's calculate. You may open the lecture notes of Uwe Hassler, if you wish, and then tell me, for an AR1 model with AR parameter rho, completely stationary, what is gamma J? Well, just feel free to open Google Hassler. So what is the covariance function of, well, remember, these are the autocovariances of an AR1 model. You started with an AR1. So then we need these. When I calculate that, then I need to plug in some value. And that I have learned 6 months ago. So you can look at this lecture note. geometry. Alright. For example, let's say if AR coefficient rho is 0.5, then the first autocorrelation is 0.5. The second is 0.5 to the power of 2. The third is 0.5 to the power of 3. The fourth is 0.5 to the power of 4. And so on and so forth. Alright. So the autocorrelation function is rho to the power of j. Right? I mean, that's autocorrelation at lag j. Right? Let's call it d. That's the
Correlation.
right. So that is the autocorrelation function. Autocorrelation function at lag j is rho to the power of j. Right? So that you should remember. Are you fine with that? Could you find it in the Uber Hustlers? Maybe I should wait so you find it in his lecture. Because you should, today when you go home, you should review his slides.
Yeah. Have the manual, but
The stochastic period, go ahead. Still further. More, let's go down.
stationary and flow here, but I don't know.
So, oh yes, exactly. Further. Oh, he used phi. Alright, so let's go further down. More. Maybe you should do the derivations because he has the general formula, but not for AR1.
Yeah.
Well, it doesn't matter. I will just tell you. So this is equal to rho to the power of j times gamma 0. Because I told you the autocorrelation times gamma 0 is the gamma j. The autocorrelation, autocovariances divided by the variance becomes the autocorrelation. If you remember, the autocorrelation is not the autocovariance. Yeah? Now we have to plug this guy in here. Alright? And then do some calculations. So that is 1 over t squared. T times gamma 0 plus twice summation j from 1 to t minus 1, t minus j, rho to the power of j gamma 0. Right, so that's sort of the variance. Right, so that you don't forget. So this guy is this. So you are all around that guy. Right? But this, I mean, I did the derivation because I wanted that you see this functional form. Because this is actually independent of whether we have an AR1 model or not. That's a general covariance, the variance of an average of a stationary process looks like so. But for an AR1 model, then we plug in the specific values, and then we go on with the calculations. All right. So what we have, indeed, is the following. All right. So let me wipe that. That's the stuff. So here what we have is that this is smaller than or equal to this quantity. Right, so this is 1 over t squared. T gamma 0 plus twice summation j from 1 up to t minus 1, t minus j, rho to the power of j, gamma 0, divided by epsilon.
Epsilon square.
Right?
Yeah.
So now, I would basically show that this converges to 0 as t grows.
So 0 for gamma. So for the first one is 0 if
That's true.
yeah.
So if this goes to 0, and this is positive, well, that's a probability.
Mm.
Right? So it is a number between 0 and 0. So it should be 0. Alright. So it means that when t grows, then the probability that this doesn't fall on the true mean is 0. Yeah. Well, that is what we have here. Good. This is an exercise. Show this, play around with that, with the geometric summation, and then show that this goes to 0. Alright, so when t grows, then this goes to 0. Do it at home. So that was a bit of a review of some of the stuff that we had here with an AR1 model. Indeed, we can have an MA infinity or ARP model and then establish this too. That would be a bit more involved. And indeed, if you want to have a general model, then you need some other tools from that. Which we can skip then for this class. So please show that this goes to 0 and t goes to infinity at home. Alright. Do you want to have a break? Or should I go till 12? So you said a yes. We can have even longer. Because indeed the number of sessions that I have is a bit longer than usual, because oftentimes people teach a bit less. But then with that, then we can have longer breaks.